Welcome to Frequency Matters, the RF and Microwave Update Series. I'm Pat Hindle. I'm here with my co-host Gary Lerude, and we have a special guest today, Dr. Amr Haj-Omar, Wireless Segment Manager at Tektronix. Welcome, Amr.
Thank you. Thank you for having me.
So you've done some very interesting academic and industry work. Can you give us a little overview of your research work prior to coming to Tektronix?
Yeah, so I started my career, or my academic career, at UC Davis up in California. I started with optical communication, a lot of DSP, and I got really interested in lab work, so I stayed behind after graduating, did a minor in economics, and got into RF. So worked under a PhD student, and he got me really excited about doing lab work. So I got a full fellowship teaching at Morgan State University in Baltimore. And there I focused on wireless and DSP, joined Texas Instruments, working on LTE technology, PLLs, as well as system on a chip. And I went back to Morgan State, where I worked on NASA transceivers and started with helping initiate a new lab that focuses on RF systems. And I'll talk a little more about that. But from there, I kind of went to the dark side, where I started doing some marketing. So I stumbled into technical marketing, even though I was a lab rat through all my career. And there I kind of started looking into automotive applications. And from there, I continued doing marketing, and I was a senior product marketing manager at Peregrine Semiconductors, where their technology on SOI and SOS for high frequency devices. And there I met my advisor, where I did most of my dissertation work at UC San Diego. And that focused on the topic of this presentation, which is flexible electronics for biomedical applications.
Quite the journey.
Yeah, and now I'm at Tektronix, as you mentioned. So I'm the wireless market segment leader at Tektronix, focusing on 5G technology.
We share some time. I spent some time at Texas Instruments like you did. So it's interesting the paths that we take.
Yes.
For your PhD, your area of research, as you said, was the fabrication and processing of adhesive-peeled flexible sensors. First of all, explain what that is and what led you to focus on that.
Yeah, so part of it was the evolution of my career. So I started with more RF front end for NASA transceivers. So there were more on the bulky side. But then I started utilizing a lot of my knowledge from semiconductors and being able to miniaturize that technology into smaller PCB that you could hold with your fingers, and utilizing technologies that are already available in the market. At the time, I worked very closely with Hussein Usman, who was in Cypress Semiconductors, and I was able to get silicon before it was available for the market. And started tinkering with the idea of building wearables that is miniaturized. And from there, Professor Todd Coleman, I can get back to this, he basically has a technology where he's able to fabricate flexible, stretchable electronics. However, at the time when I saw his demo, it was all wired. So what made sense is for this to be wireless, especially that it should be something that is seamless, that you could apply on your skin, and pretty much to replace almost like a bandage. So that's kind of how it all started.
So what type of sensors would be incorporated into these adhesive packages, and what type of measurements would they make?
So what I went with was Bluetooth low energy. programmable system on a chip. The different sensors that I applied were for respiration. So it was a string gauge connected to a comparator. So every time you breathe, we have a Wheatstone bridge that's connected to the comparator. So it lights an LED and you're able to collect your frequencies in terms of breathing. And it has a temperature sensor. And this was a part that I defined at Texas Instrument as a system engineer, which has the lowest temperature accuracy, as low as 0.1 degrees Celsius, which is important because that's the American standard of test and measurement. And then there's a UV as well as the ability to do EKG.
So if you look at the end-to-end processing for that, you mentioned Bluetooth Low Energy. Would that still be the wireless connection? And then how would you accumulate the data and process it to analyze it?
Good question. So the Bluetooth Low Energy has a programmable front end. So it has 2 ADCs. It has a number of op-amps, which I utilized for my EKG. So this would be a block diagram. And the idea was to have a modular approach where the only thing I have to change was my sensor. And the fact that it was a programmable front end, it enabled me to flexibly change the sensor without having to change my RF front end as well as my RF transceiver. So I start with the sensors, as I mentioned. It could be an EKG, respiration, temperature sensor. I have an analog front end. Then I have my Bluetooth Low Energy that's powered by a lithium battery. And then I have a matching network that connects to the antenna. So a lot of the work and patents that I worked on is related actually to the antenna design. And one of the challenges is the human body is a bucket of water and salt. So it does exactly the opposite of what we need when we transmit, right? Instead of transmitting, it actually soaks. So that was part of the challenge, to have the antenna work while it's actually applied on the skin.
So can you describe the process you came up with and the benefits to the approach that you took?
So I started by simulating an IFA antenna. I chose an inverted F antenna as it's a well-established antenna for Bluetooth. And initially I started with a gold ground plane. And as I started simulating, you could see the red is where you have most of the active radiation, and the blue is where there's less activity. And then the one challenge was, since it's solid, it's not going to be able to be stretchable. And being stretchable is an important aspect because our skin is stretchable. Adhesive that I showed is Tegadurum, which is a FDA adhesive that's applied if you ever had to draw blood or what so, and it allows for stretchability. So in order to add flexibility, what I did is I applied those fractal designs, putting in mind that there is a distance which is much, much, much smaller than the wavelength. And I was able to get the same effect when I had a solid ground plane. So my simulation basically showed similar activity, whether I'm using a solid background or having a fractal design. From there, I actually took it inside an aquatic chamber. So that's actually me inside the aquatic chamber, applying it on skin. And when I simulated the skin effect, As I mentioned earlier, the body will absorb the radiation, so it has to be compensated um, to radiate outwards. So this is the radiation pattern measured versus simulated. Then I started doing some tests in terms of stretchability to see if the radiation pattern and the reflection will change. And I was able to stretch up to 30%, which is more than what our skin could stretch, but still be able to radiate at the frequency of that I needed. One thing that was really interesting too is as we applied these antennas for different applications for patient compliance on medicine bottles and different materials, the frequency will shift. And the mitigation for that was pretty simple. It was just by using a scissors and be able to literally change the length of the antenna.
Well, you've given a new definition to the term skin effect. So if we look at, you've talked about some of the challenges with the sensors and also the need to match the antenna. If you look at all of the challenges you faced, what would you say were the hardest ones to overcome?
I think one was the antenna. It was unknown, and there wasn't a lot of work that's been done in this area. And I think the ability to use the fractal design to make it stretchable. But there's even a more interesting application that came out of this, which is the early work of Todd Coleman, who was my advisor. When he started using fractal, he used it for EKGs. So there was another reason why I wanted to explore this, which was the ability not to just use it for stretching, but also so I could use it as a sensor to collect EKGs and EEGs.
So what is the future of this technology that you see, and how can it be beneficial to treat different things?
So I would say the future of the technology is, imagine now whenever we go to a doctor, we get our blood pressure at that moment. Typically goes up since we're worried about what the numbers will look. But more importantly, what if you could give your doctor continuous monitoring, right? He's able to see your chart for the last 6 months. Even better, with the ability of having broader bandwidth and 5G, it enables us to be able to take a lot of data into the cloud, have AI, artificial intelligence, where you could take the data, set alerts if your temperature is beyond a certain point, your vital signs, and be able to make decisions, or even better, allow your doctors to be alerted if there's something out of the norm. So especially now with the whole COVID and how it's affecting a lot of minority communities, what's missing is the data. If we have better data, we will be able to understand why certain communities more receptive to COVID than others. So I would say this is kind of the future of it, and more importantly, to help in behavioral decisions, right, for preventive medicine.
If we go back to the discussion you had earlier about your timeline, your career path, you mentioned that you were a professor for a number of years, and we understand you were involved quite a bit in diversity and inclusion, trying to encourage students to pursue careers in science and engineering. Tell us more about that work, and if you're optimistic about the progress that's being made.
Yeah, so part of my research involved a lot of undergrads, and that was something I learned from my early days at Morgan State while I was teaching. So Morgan State had a very unique culture when it came to involving undergraduates in research. The ability to get them excited about research and science and what so. So part of my work, I actually took my research into the classroom, where I had a little grant from Intel, and what I started doing is starting with a social problem. As I mentioned earlier, for example, high blood pressure is a big part of the challenges in African American communities, and this is something that kids in the room are interested in. They could relate to, and from there start to come up with solutions to solve the problem, and then get indulged into the details of the sensors and building amplifiers and filters and programming Arduino boards, and even bringing EKGs to the room so they could see their EKG. And through my years of teaching, I figured that that's a much more better strategy than hitting them with electromagnetics and circuits right from the bat. Um, in terms of taking this class further, I was able to actually take the same class and pretty much make it more digestible to students. So I took it from an introduction to engineering class into high schools, into a refugee community in San Diego, a couple of middle schools, and even back to Morgan State. So I think it's pretty, I would say that was me giving back to my community.
Wow, that's quite the academic background. So now you're a wireless segment leader at Tektronix, and you're working on some 5G systems and other things. Can you tell us about that work and what you're doing?
As you all know, there's a lot of need or unmet need when it comes to the new standards with bandwidth and instrumentation and measurements. So with 5G, now you have up to 800 megahertz of bandwidth. With Wi-Fi 6E, you have up to 1.2 gigahertz of bandwidth. And with consumer premise equipment that's replacing Wi-Fi transceivers into our homes, there is multiple transceivers. If you look at the block diagram of a CPE for Wi-Fi 6, Wi-Fi 6E, 5G, as well as a lot of digital components through the CPU. So a traditional spectrum analyzer is limited to one channel. It's limited in terms of bandwidth. So our scopes. So we've seen a trend where there is a shift from spectrum analyzers to scopes, and the trend is mainly because one, you're able to address the MIMO need because of the multiple channels, and the advancement in hardware of a scope allows you to have up to 2 gigahertz of bandwidth, which meets the standards, whereas spectrum analyzers are limited to 800 or 1 gig. So that's one thing that's being addressed, as well as it being a Swiss knife, where you're able to look at digital wired protocols such as USB or UART or even DDR5. In addition to that, there's a digital down converter in each channel. And what that means is you're able to have time domain and frequency domain totally independent, and you're able to correlate between your frequency and your time domain. So today we're able to actually have 5G NR systems embedded in a software we call Signal View on our scope. And that allows you to do EVMs of 1024 QAM And we've been able to see numbers as low as 0.3% EVM. So we believe this would be the future in terms of the 5G setup and RF engineer, as well as we're starting to see trends in terms of OTA, over-the-air test measurement. As I showed in my dissertation work, I had to take my antenna, my setup into an acoustic chamber, but now with much higher frequencies, you're looking at FR2 millimeter wave, the antennas are designed into the silicon. So there's the challenge now of being able to probe over the air in your R&D setup. So that's something that we have solutions that we're developing on as well.
This has been quite a wide-ranging discussion. Have we forgotten any points that you'd like to cover?
If you'd like to see a demo or you want to talk more, feel free to contact me. It's amr@tektronix.com, and it's been a pleasure.
Well, thank you, Amr, for joining us. It's been a really interesting conversation hearing about your background and the work that you're doing, beginning with flexible sensors and skin and biomedical applications, and now moving into 5G test and measurement. And so we'll be interested to hear more about your work as the time goes on. Thanks again.
Absolutely. Thank you for having me.